ones are going to be a little more complicated than the ones that we saw last class. We're going to be combining a little bit of the concepts that we saw on the first or the last couple of months. So they're kind of long, but they're good. They build character. So before that, does anyone has a question about the homework? And also online, if you guys have any questions about the homework. Nope, Barry? Number 7. Oh, crap. Anyone has a problem? Oh. Here. I have purpose. Okay, number 7. You don't there. This is going to be number 7. Is find the stress on a bone. Has 1 centimeter in radius and 50 centimeters long, and supports a mass of 100 kilograms. Find the strain and find the Young modulus. Okay, so we have the bone, and I'm gonna just simulate the bone as a cylinder, just to make the calculations easier. And I know that the radius is 1 centimeter, and the length is 50 centimeters. The force is going to be 100 kilograms times 9.8. That's going to be the force that's going to be supporting. And I need to calculate the stress, strain, and the Young modulus. So, and I know that under this force is going to be compressed by 0.15 millimeters. Okay? So, so first, I'm going to calculate the stress. The stress, the way we define it, is basically force divided by the area. And the area will be the area in which the force is being applied. So it will be that area over there. So we're going to have the area is pi r squared. So this will be pi times 0.01 squared. So I'm going to put everything on meters just so I can divide by the newtons and all that. So I'm going to end up with an area of, I think it's, what, 3.14 times 10 to the minus 4. Yeah. So it's going to be 3.14 times 10 to the minus 4 meters. So from there I can calculate the stress. The stress is going to be 100 times 9.8 over 3.14 times 10 to the minus 4. And I end up with a stress of 3.12 times 10 to the 6 Pascal. Yep. So that will be the stress. The strain is delta L over L. So that's going to be 0.15 millimeters. So it's going to be 0.15 times 10 to the minus 3 meters divided by 50 times 10 to the minus 2 meters. So this will be 3.0 times 10 to the minus 4. And the Young modulus is just stress divided by strain. So this is 3.12 times 10 to the 6 over 3.0 times 10 to the minus 4. So that would be like 1 times 10 to the 10. Yeah. 1 times 04 times 10 to the 10 pascals. Okay, and Morgan wants 4, part A. Okay, I think 4, part A. So 4A, this was 7. 4A, somehow similar. We have the Achilles tendon, and the Achilles tendon, again, I'm going to simulate there's just like a very long wire. It has a cross-sectional area of 110 square millimeters. It has a length of 15 centimeters. The mass of the runner is 70 kilograms. Okay, and I want to find out what is the contraction, or what is the stretch when the force is 8 times the body weight. Okay, there is one piece of information that is missing. That is the Young modulus of the Achilles tendon. I think that's in your textbook. I don't know if anyone, do you have the value?
I couldn't find it. 0.15. Right?
1.5.
No, 0.15.
0.15 times 10 to the 10?
Yes.
Yeah. Okay, so the force will be 80 times 70 times 9.8. That's going to be the force that's being applied. With the calculator, there is. That's going to be 5,488 newtons. The area, we need to convert the area from millimeter square to meter square. So 110 millimeter square, I know that 1 meter is 1,000 millimeters. I'm going to square. Bless you. And that's going to be 1.1 times 10 to the minus 4 meters. Okay, so with that, I can calculate this, the stress. It's going to be the 5,488 over 1.1 times 10 to the minus 4. That's going to be 4.99 times 10 to the 7 pascals. And then to calculate the change in length, I know that, what is it? The Young modulus is the stress divided by the strain. So from here, I know that the strain is going to be the stress divided by the Young modulus, and the strain is delta L over L. And if I need to solve for L, delta L, so delta L will be just sigma over Y times L. So then I can substitute the values that I have so far. So I'm just going to do it over here. I'm going to have stress is 4.99 times 10 to the 7. The Young modulus is 0.15 times 10 to the 10. And L is going to be 0.15 meters. Hmm. 4.99. Oh, well, yeah, makes sense. 4.99 times 10 to the minus 3 meters. So that's around 5 millimeters of stretching. Okay. Questions? No problem. Okay. So before I forget, there's a quiz due on Monday. It's a quiz about momentum, and it's basically concept questions, so very similar to question 2 of the homework. So the quiz is going to be problems like that. So just don't forget. There are 5 questions, but the last one is it doesn't have any points, so it's just more like a question about the class and things like that. Okay, so back in the day, one way to do ballistic analysis, one of the things that you want to do when you're doing ballistics is to try to figure out, hey, Brian, how you doing? Good. I didn't see you. You've been so quiet. Hello. One of the things that you want to do is to figure out what is the velocity of the bullet at the time of impact. That can help you try to figure out how the fragments are going to be dispersed, or that can help you determine the kind of weapon that you are talking about. Right now, you can measure those velocities in a lab with a high-speed camera, but before you have those cameras, then there was not an easy way to directly measure the velocity of the bullet. So the only way that you could do this ballistic analysis is by what we call either a ballistic pendulum or shooting bullets to a block. And it was a way to indirectly measure the velocity. So this is one example of how those things work. So imagine that you have a block, and for sake of argument, I'm going to say that this block has a mass of 10 kilograms. And the block is going to be static, so the initial velocity is going to be 0. So there's no momentum on this block. And I'm going to place this block, obviously, on a surface. And what you can measure, one of the things that you can estimate is what is the friction coefficient between the two surfaces. So you know this friction. So for this example, I'm going to assume they have a friction coefficient of 0.3. Okay? Now, I'm going to shoot a bullet, and I know the mass of the bullet. This is something that I can measure in the lab. And I'm going to say that this bullet has a mass of 10 grams, but I have no idea what is its velocity. Okay, that's what I want to find out. I want to determine what is the velocity of the bullet. Now, you shoot the bullet, and the bullet gets embedded on the piece of wood, and the bullet is going to push the block forward. And something that you can measure is what is the displacement of that block. So you can imagine the bullet inside the block, and you can measure this distance. And let's say, for sake of argument, that this distance is 7 centimeters. Okay. So the question is, if I know the mass of the block and I know this distance, can I predict what is the velocity of the bullet? Okay. So this was the old way to calculate or estimate velocities of bullets. The other one was very similar, but instead of having the block on a surface, it was the block hanging from a wire. You shoot the bullet, and then the block is going to do like a pendulum motion, and you can estimate the velocity of the bullet depending on the angle of deflection. So we're going to do it like this. Okay. Now this is a more complicated problem, and it's going to take a while to solve it. So hang in there. The problem can be divided in two parts. Okay. The first part is the bullet hitting the block. Okay. So you can imagine that it's going to be somewhere around there. So that's going to be the first part of the problem. The second part of the problem is once the bullet is inside the block and the block starts moving, the block is going to start slowing down because of friction until it comes to a full stop. So you can imagine that we're going to have a second problem over here. Part number one involves conservation of momentum. Part number two is just forces and accelerations that were what we've been talking for the beginning of the semester. Okay. In this particular case, because I don't have this velocity, I cannot solve the conservation of momentum first. I need to start with section number two, and then I'm going to move backwards until I calculate the velocity of the bullet. Okay, so I'm going to do section 2 first. And for section 2, the problem, you can say, okay, I have a block that has an initial velocity and is moving until it comes to a full stop. So the final velocity is going to be 0. And it's moving in 7 centimeters. I'm just moving 7 centimeters. So I know that the initial velocity has to be different than 0, because if it were not different to 0, then the block will not move. Okay, so I know that velocity is going to be equal to 0. It comes to a full stop, so I'm going to have an acceleration. Okay, there's one equation that can help me relate these three quantities. It's not an equation that we use a lot. We used it like a month ago, so I don't expect for you guys to remember it. But that equation, it looks something like that. Final velocity squared equals initial velocity squared plus 2 times delta x. So I have the final velocity is going to be 0. I don't know the initial velocity. That's what I want to find out. I have delta x that is going to be 7 centimeters, but I don't have the acceleration. Now, I can find the acceleration, okay? So to find the acceleration, I'm going to do the free body diagram. I forgot the name. I'm going to do the free body diagram of the block. So the free body diagram of the block. Mary.
Can you move it up a little?
How many forces do we have?
Oh boy, I'm not ready for this question. 4.
Which ones?
The normal force, the force of the weight, the friction force, and then the applied force.
Which one is applied force?
I mean, like which way?
No, which one is?
The bullet.
So here's the thing. There's no applied force. At the moment that the bullet pushes the block, that's it. The bullet comes to a full stop, and it's not constantly pushing the block. So you're only going to have 3 forces. You're going to have the normal force, you're going to have the weight, and you're going to have friction. And that's it. Okay? There's nothing else that's pushing forward the block. If they were kind of like a rocket or something that will be, or a hand that will be pushing the block. But this will be like kicking the turtle. Do we do it? Kicking the turtle? Yeah, so it's like kicking the turtle. You just hit it, and that's when you give it the push, And that's it. The projectile is going to start slowing down as it travels to the ground. So it's pretty much the same idea. So sum of forces in y are going to be equals to 0. The normal force plus the weight is equals to 0. Normal force minus mass of gravity equals to 0. So the normal force is mass times gravity. Okay. In the x direction, we know that the block is slowing down. So there's going to be an acceleration. So we're going to have that the forces in x have to be equals to mass times acceleration. But the only force that I have in x is going to be friction. So the friction is going to be equals to mass times acceleration. And for kinetic friction, we know that it's going to be negative mu k times the normal force equals mass times acceleration. So this will be mu k mg equals ma. I notice that it really doesn't matter how big or small the mass is. The only thing that we care is that friction coefficient and gravity. So the acceleration is going to be negative mu k times gravity is going to be 0.3 times 9.8 negative. And that will be it. Negative 2.94 meters per second square. Okay, so now that I have this acceleration, then I can go back to this equation over here, and I can find what is the initial velocity of that block. So I'm going to write it over here to a delta x. Remember, the final velocity is going to be 0 because we want to calculate when the block comes to full stop. And I'm going to have bi squared equals minus 2a delta x minus 2 minus 2.94. It's 0.07. So this gives me 0.42, and the square of that will be 0.64 meters per second. Okay, so remember, this is the velocity of the block and the bullet after the collision. Okay, so now that I have that velocity, now I can go to the first part of the problem and I can try to do the conservation of momentum. So conservation of momentum, I'm going to have the mass of the bullet, the initial velocity of the bullet, plus the mass of the block, the initial velocity of the block. That's going to be equals m1 plus m2 final velocity. This final velocity over here is this 0.64. This is the velocity of the block and the bullet after the collision. This is going to be 0. So okay. It makes sense. It makes sense that this velocity is the same as this one. Even if the name of the variables is a little bit different, they represent the same thing. It's the velocity of the block of the bullet after the collision. So from here, I can find the initial velocity. That's going to be the 0.01 grams, times the 10 kilograms over 0.01 times the velocity, which is 0.64. The mass of the bullet is so small compared to the mass of the block that you can almost ignore it from the top part of the equation. I'm going to leave it just so you guys know what happened to that mass. That's not always the case. And from there, I get a velocity of 642.2 meters per second. That was pretty cool.
I don't think I'd be able to do it by myself.
But we have seen all the equations. So technically, yes, you should. This was a question for an exam, by the way. Not to put you nervous, we're still going to have more time. Okay, does it make sense? There are a couple of things that you need to, that I want you to get from these kind of problems, is that you can divide the problems in different sections. So you don't need to use one equation to solve everything. The whole point is that you can divide in sections. Each section can be semi-independent from the other ones. They're going to be variables. They're going to be they're going to be connected in the different sections, and each one can have its own set of physics equations that we need to solve it. Okay, does it make sense? Ish. Okay, you want to try one? Everybody says like, nope, I'm done. We're gonna do it anyway. So, same idea. You have a bullet. You have a block. The mass of the block is going to be 5 kilograms. It's at rest. The static coefficient, the static friction coefficient is, the kinetic friction coefficient is going to be 0.2. The mass of the bullet is going to be 20 grams. And the velocity of the bullet is going to be 500 meters per second. Okay? And what I want to find out is how much it moves, how much is going to translate under these conditions. Okay? Make sense? That hurts. Now, in this case, in this problem, because you have the initial velocity and masses of the two objects, of the bullet and the block, you can actually start with the conservation of momentum, and from there you can start doing the Newton's law second. after. Aaron, the mass of the bullet is 20 grams.
In this case, again, you assume that the bullet gets stuck in the loop. So to travel the same. So it's 5 plus to 1 plus 2 will be the same. This. So at the moment that you are working on this powder column, this will be the initial velocity of the block. The block and the bullet. This will be the final velocity of the block and the bullet. Yeah?
Okay. Alexis, Russell, can you show me your work? She's ignoring me. Oh, no, there she is. Yeah, you got the acceleration correct, and okay, you're still working on the other part. Good.
So is the initial velocity the 500 meters per second?
That would be the initial velocity of the bullet. But once the bullet gets inserted in the block, then it will be something completely different. And you need to calculate that velocity to do the second part of the problem. What you got?
I don't know if I'm done or where I'm at. I got this, which would be my acceleration.
No, the acceleration.
Huh?
Yep.
And then I tried to do this part, but we're looking for the delta x, so I think 500, but I don't think that's right.
No, you need the acceleration. And this VI will be the velocity.
Is it going to be 0?
No, it's going to be the velocity of the block and the bullet after the collision.
How do you solve for that? Yeah, how do you do that?
Okay.
That's wrong.
So, you got it correct?
No, I didn't get that.
No?
Yeah, I can figure it out.
Okay. So many of you start from, you follow the same step that we did in the previous problem, which is fine. And at the end, you end up, and we can do it that way. Alex, what you got?
Like my delta x?
Yeah.
I got 0.51.
0.517.
517.
Oh, okay. So we're gonna do it like that. So it follows more or less the procedure you've been doing, but it's not the only way you can do it. So I'm gonna be working with this part from the block, the bullet moving until it comes to a full stop. Okay. So the equation that I'm using is gonna be this one. And again, I know that the final velocity is going to be 0 because I need that thing to come to a full stop. I don't know what is that initial velocity. I need to find out what is acceleration. So to calculate the acceleration, I do the free body diagram. I'm going to have the normal force. I have the weight. And I have the friction. From the sum of forces in Y, I end up that the normal force is going to be equals to mass times gravity. And from the forces in X equals mass times acceleration, I have minus mu k mg equals ma. And the acceleration is going to be minus mu k times gravity. So that's 0.2 times 9.8. And that's what, 1 point. Say that again?
1.96.
96 meters per second square. Okay? Everybody got that? I think that's where everybody got stuck. Now, you have the final velocity, but you don't know this velocity, this initial velocity. Now, this initial velocity is the velocity of the block and the bullet after the collision. Okay? So what I'm going to do to find that velocity is to look at the conservation of momentum. So the conservation of momentum says, okay, I have the bullet, the momentum of the bullet moving at 500 meters, plus the momentum of the block, which is 0, and that has to be conserved. So I'm going to have the two masses moving at the same velocity. This final velocity, this is the velocity of the block and the bullet after the collision. It's a little bit confusing because we only using initial and final, and we use that for every section of the problem, so it can be a little bit confusing. One thing that you do is that this can be velocity. You can add like a super indices just to indicate what section are you guys stuck in. But it also gets a little bit complicated. I don't know if it really helps. And then you can say that, okay, that velocity is the same as this velocity. If that makes any sense. If it doesn't, just try to understand what each one of these velocities means. So I'm going to solve for this final velocity. This is going to be 0. And then the final velocity is going to be m1 initial over m1 plus m2. And this is a 500. So this will be 0.02 times 500 over 5.02. And this gives me a velocity of 1.99 meters per second. Okay, and this is the velocity that I'm going to be using over here. Okay, so I'm going to have 0 equals 1.99 squared plus 2 as 1.96 delta x. I'm running out of space. Okay. Negative 1.99 squared equals 2 times negative 1.196 delta x. Two is 1.96. And I get 1.1 meters. Okay, so the block will move 1 meter before it comes to a full stop. Yeah. Rihanna, makes sense now? Now, I said that you could do it a different way because you have the mass and the velocity of the block, and you have the mass and the velocity of the bullet. You can calculate the conservation of momentum. You can do this section first, get this final velocity of 2 meters per second, and do the second part. Yeah, that's the most direct way to do it. Okay, Tatum, make sense? Grace, Ish, 1 meter.
What did you do for acceleration?
For acceleration, I use 1.96. Okay. Any questions? No? Any questions on the chat? I guess not. Nope. Again, are you ready for another problem?
Sure.
That's not the answer that one. Alex? Silent? Okay. I was Sylvia, thank you. Yeah. So Sylvia, do you want to go home? You missed your chance. So the section in the morning we were running late, so I was able to catch up with them. So we are both sections are the same cover the same material. So for you means that you leave 10 minutes earlier. So have a great weekend and see you guys on Monday. Thank you.
Well, I never know, because sometimes you have to talk about problems. What am I supposed to say? I'm gone. It's Friday. No, that was one that I was going to ask. Because I did it today. That's good.
Sure.
The Excel's on Canvas though. For the first one.
Okay.
Because I couldn't get it printed.
Okay.
So it's just in two separate spots.
That's okay. That's okay.
I have a question.
Sure.
Yeah. So for the homework number 7, I did it before class, and I got the same stress and strain, but I got a different young modulus, and I used a different equation than you did, and it's like the same number, but it has like the same numbers, but like
Yeah,
wrong
different.
decimal placement, I guess. So like, and I like ran it through your way and my way in the calculator, and like I just don't know where it's going wrong.
So the strain is the same, right?
Yeah.
I don't know why. She does more than Jeff does to the fish, and I wish I could just sit there and watch it like Jeff did it.
Number 7. So we have the same stress, but the stress is different.
It's just, it's this,
Your area,
what is that?
yeah, so you calculate the area as
And I put a different number.
3.14, and then you put this one.
Okay. That makes sense.
Yeah, I don't know where you got this one.
From this, I had to redo this one, and then I had to redo that one after, so I think I just like,
You just copied. Yeah.
Yeah.
So the problem is your area.
okay.
So here will be the 3.14 instead of the minus 4.
Okay, so I just flipped them.
Yeah.
I have to resubmit this whole thing. I submitted it before class.
Oh.